Hello everyone. In this video I'm going to cover the concept of dynamic programming using the problem Stone Game 3. So I'm going to tell you the step-by-step procedure how to approach a problem, starting from the most easy recursive solution to the most optimized dynamic programming solution. So please go to the entire video to see how to approach this problem during an interview. So let us see the problem statement. The problem statement says that Alice and Bob continue their games of piles of stone. There are several stones arranged in a row and each stone has an associated value which is an integer value. Alice and Bob take turns while Alice starting first. On each player's turn, the player can take 1, 2 or 3 stones from the first remaining stones in the array. The score of the player is the sum of the values, the stones he has taken. The score of each player initially is 0. The objective of the game is to end with the highest score, and the winner is the player with the highest score, and there could be a tie as well. The game continues until all the stones are being taken. Assume Alice and Bob's play optimally. We have to return Alice if Alice wins the game, Bob if Bob wins the game, and in all the other cases we have to return tie. So let us see the example. The stones are 1, 2, 3 and 7. Alice will always lose. Her first best move will be to take the 3 piles, that is the first 3. The summation will be 6. Now the score of Bob is 7, so Bob wins in this case. Then if we go to the next one, alright, so we can have the negative values as well. So in this case Alice wins. Alice must choose all the 3 piles at the first move to win and leave Bob with the negative score. Okay, in this example there's a tie, so I think I should go for the first example, 1, 2, 3 and 7. So what I'm going to do is I'm going to make a helper function. So this function will return me the optimal move. So let's say I'm going to play the game. So I will be having 3 options: to choose 1 stone, to choose 2 stones and to choose 3 stones from the start. So I will try to choose 1 stone, 2 stone and 3 stones and then see which one gives me the most optimal solution. So let us say the array which is given to me is 1, 2, 3 and 7. Now I have 3 options, so I will get 1 in this case because I'm only choosing the first stone, and the remaining array will be 2, 3 and 7. This array will be passed on to the next player. So the next player will be playing with this, so this will get subtracted from 1. So this is my first option. My second option will be to choose the first 2, so the summation will be 3 and the remaining array will be 3 and 7. Now this array will be passed on to the next player and he will make turn using this array. So this will get subtracted, and this is the second option that I have. The third option that I have is to have the summation of the first 3, which is equals to 6, and then pass the remaining to the next player. So this is my third option. Now, so this is what the current player is having, the second player. Now second player will be playing optimally, so he will be having 3 choices. The first choice will give him 2 as the summation, the second choice will give him 5 as the summation, and the third choice will give him 12 as the summation. The array remaining in this case is 3 and 7. The array remaining in this case is 7 only, and here the array is empty. Now if we expand this, so this will also get branched in 3, actually only in 2 because we are having only 2 stones. So we are choosing the first stone only, 7 remains. Then we are choosing the first 2 stones, which gives us 10, and the array is empty. Now in this one we don't have any further option of branching because it will give 7 itself. We are choosing the first stone. So from here the answer that we will be getting is -1. From here the answer is 10. From here the answer is 3 minus 7, which is equals to -4. The optimal is 10, so 10 will be returned. 3 minus 10 is -7, so -7 will be returned. From here, okay, we can further expand this. By expanding this, we will be getting 3 as the summation and 10 as the summation and an empty string, while here 7 remains. So this will return us -4 again. So the answer in this case is -4 and in this case is 10. So we have to return 10. We're returning 10. 2 minus 10 is -8. The first option will be -8. Here the option is 5 minus 7, which is -2. Here the option is 12. So we will be returning 12 from here. And 1 minus 12 is -11. So -11 in this case. So these are the three options. All of them are negative. So in this case, we can say that this was the move given to Alice. Alice has 3 possible options. Those options are -11, -7 and -1. The best among these is -1. So the final score of Alice is -1. This score is Alice's summation minus Bob's summation. So it basically shows that Bob can collect more number of stones than Alice. So always Bob wins the game. So this was the recursive solution. So one thing that we notice here is that there is an overlap. So where did we see the overlap? The overlap was found here. Okay, so the overlap was here. 3 and 7 was the remaining. 3 and 7 here also it was remaining. Then 7 was remaining here. 7 was also remaining here. So these were certain overlaps which we could see. So we now have a slight hint of dynamic programming here. Now first we look at the code, how to code this problem using recursion. Then we will try to optimize our code using dynamic programming. So let us move on to the coding part. So as I told you, I am going to create our helper function, which is going to return us the optimal solution for a particular player. So this is my helper function. I will be passing on, okay, let me change the variable name to s, vector of string v to this, and an integer I. So this I denotes us the first position of the first stone. So initially I is 0. So this is I. Initially I is 0. In this case I is 1. In this case I is 2. In this case I is 3. So this is I is denoting us the starting point. If I is greater than equals to s dot size. In this case there are no stones remaining, so we have to return 0. Else we have 3 options. So let us initialize our answer as int min. We are going to optimize our answer, so we are initializing it with int min. So answer is equals to maximum of answer comma s of I, because we are taking the first stone, minus the I plus 1. So we are passing on the turn to the next player. Next we have if I plus 1 is smaller than s dot size. So in this case we can have another option, maximum of answer comma s of I plus s of I plus 1 minus help of s comma I plus 2. The third option would be if I plus 2 is smaller than s dot size. The third option is adding the first 3 values. Okay, so we have to return answer. If we call the same function for ls, int ls is equals to help of s comma 0. So this will give us the difference between Alice's score and Bob's score. If this score is greater than 0, that is Alice have more number of stones, we have to return Alice as the answer. If this is equals to 0, that is there's a tie. The last option is that Bob wins the game, so we have to return Bob. Okay, so this is the problem. I think now we should compile. Alright, so we are getting correct answer for this test case. Let us try to submit this. This should give us time limit exceeded. Alright, we are getting TLE. Now, moving on to the next optimization, which is to convert this recursive solution into a top-down dynamic programming solution. So we are going to create a DP array of size. What were the constraints given? Constraints were 50,000. So we are going to create this DP, then initializing this DP with -1. If the DP of this I is not equals to -1, we have to return DP of I, because the answer is already present, and simply storing the answer for each I. Let's see if it works. Alright, it is working. So we see that the solution got accepted. Now once we are done with this, we are going to convert this problem from top-down dynamic programming to bottom-up dynamic programming. For this we need to see that how this DP array gets filled. So this DP array is getting filled for I which is greater than s dot size, the DP is 0, the answer is 0, we can say that. Then for each I we are using the DP for I plus 1, the DP for I plus 2, and DP for I plus 3. So to fill a particular DPI we need 3 DPs, the I plus 1th, the I plus 2th, and the I plus 3th. So now we are going to convert this. We are creating vector of int DP of n plus 1 size and initializing this with 0. Then int I is equals to n minus 1, while this I is greater than equals to 0. We can simply copy this code. and try to make changes in this one. So instead of help, we will be using dp of I plus 1, dp of I plus 2, dp of I plus 3. Finally, this ls is dp of 0. The rest of the code remains same, and we are getting rid of this part. Okay, so we forgot to do I minus minus. So it got accepted. The next step is to see for further optimization. So what we are doing here is to fill a particular dp. To fill a particular dp, let's say to fill dp of I, we need dp of I plus 1, dp of I plus 2, and dp of I plus 3. So these are the only three things we need to have. So even if we have a dp array, so let's say this is the dp array and these are the entries. To fill this particular entry, we need this one, and this one. This one is not required. To fill this one, we need only these three, and the rest of them is not required. So anytime we are going to require only these three. So instead of creating the entire dp array, which could be as large as 50,000, what we can do is we can simply have three variables. So instead of using so much of space each time, we can solve this in constant space. So we are going to optimize this. We are keeping, instead of this, we are keeping only three variables. Int, let's say this is I1, this is for I2, this is for I plus 2, and then I plus 3. So these are the three variables which we are going to keep. All of them initially is 0. We will be using I1. In this case, I2. And in place of dp3, I3. I3 will be equals to I2. I2 will be equals to I1, and I1 will be equals to answer. This is basically in this case this is I1. So we see that we used constant access space and we were able to solve this problem. So the steps that we saw were, first one, the recursive solution. The second one, top down. dynamic programming. So we adjusted the code accordingly. The third step was to convert from top-down dynamic programming to bottom-up dynamic programming. Bottom up. Then from bottom up, the final step was the optimization, space optimization. So these are the 4 steps which we need to follow to approach any dynamic programming problem during an interview. You have to go from the recursive to the dynamic programming to the bottom up, and from bottom up finally to the optimization. The final solution was constant space solution. This was in terms of space, and big O of n in terms of time. This was big O of n in space and big O of n in time, and top down was almost the same. It is bottom up is slightly more optimized, but the complexity is same. So if you like the video, please subscribe to the channel and please share it with your friends. Thank you.